Cucco. Thank you so much for coming on the show.
Yeah, it's my pleasure. It's actually very funny because it's my first time in a podcast. Yeah. So I had no idea what to expect. So hope it's gonna be a nice search.
I hope it's a good first impression.
Yeah. Definitely.
How are you doing today?
I'm very good. Still getting used to the climate here. In Texas, it's very hot right now. Still hot in Brazil as well, but here is a little bit more humid, so it's a bit complicated to deal with.
Really, it's more humid?
I think so, than my region at least, yeah.
Okay. Yeah, I guess Brazil is a huge country.
Yeah, it's a huge country. I come from the very south, which is actually the coldest part of Brazil as well.
Yeah. Yeah, at that point you're getting pretty far from the equator. Yeah, and then you have I didn't think about that, but your summers are winters.
Yeah. It's quite right now it's actually kind of cold there because it's July, so my family's complaining. Yeah.
I guess I'm curious, was it a little bit weird coming to the US and then January to us is a really cold month, where January to you in your part of Brazil might be a little bit warmer?
I think it was okay because since I moved from Brazil to France first, I kind of had to change my the climate, and I think France is kind of similar to here more or less. So it's much colder though, but the way the seasons are, I think it's better.
Yeah, so you seem to have this really, like I was saying earlier, you have this really rich international experience and this really rich international journey, starting out in Florianopolis.
Yeah.
Yeah, Florianopolis, and then you go to France and then Belgium, and now you're here. And I'm curious how on that journey, how you kind of came to the point of Perovskites and optoelectronics, and kind of what led you into the niche category of research that you are in today.
That's actually kind of funny because it was not random, but it was sort of random. I started during my undergrad, I didn't know what I wanted to do after physics. So I was doing a little bit of everything. I did experimental physics, I did cosmology, I did everything, just to see a little bit of every possibility. Yeah. And when I went to my master's, I started doing classes, and we don't have to choose the supervisors instantly. So I started looking around and talk to different people, doing some small projects, and eventually I fell in this one that's related to this computational physics, materials physics that I do. And then after that, the PhD was just a jump in the same field, just a different object. I just changed the material to Perovskites, but it's the same field, same tools. Yeah.
Gotcha.
So it's kind of natural, I guess. But
and this was in France?
Yeah. I started working with Perovskites in France. Yes. During my master's, I was doing also computational physics, the same tools as I was doing on my PhD, but for another class of materials, these topological isolators.
Oh, okay. What are those exactly?
Yeah. So they're kind of interesting because they're if you imagine the bulk material, a square if you want. Inside the material itself, it's an isolator, so it doesn't there's no charge moving inside the material. On the surfaces, there are charges moving.
Oh, that's
so the net charge is actually zero because you have each spin going to a different direction, but still you have charges that you can measure on the top.
Yeah, that's exactly a problem that I had in my physics class in high school, where we would do Gaussian integrals of idealized substances that have charge only on the outside of them, but they're perfect insulators inside.
Yeah.
It's amazing that you guys can create a material like that.
Yeah, I guess it's a pretty recent. People are doing models for these things for many years, but the actual, let's say, computational part came much later, in the 2000s probably.
And so you're not necessarily creating the substance itself, but you're modeling the different atoms within the substance and creating a computational.
Yeah, you kind of have both aspects, because you can think about investigating a material that already exists. So people can go to the lab and do some refinements and get the crystal structure, and then you can do some calculations and try to figure out some properties, But you can also think about trying to develop new materials, very alchemy way. You can just propose something, and you can propose show that it's stable chemically, mechanically speaking, and people can try to synthesize. And these things actually happen, so it's pretty interesting.
Yeah, there's got to be a balance between functionality, but then also ease to make.
Yeah.
I wonder, like, when you go to conferences and people are giving you all these crazy new materials that they've kind of theoretically discovered, how many of those are like, this is really cool, this is awesome, but there's no way we could ever make this like large scale?
Yeah, I mean, there's actually a lot of technologies that are kind of like that. I don't know. For example, I've been working a lot with solar cells and LEDs. And I don't know if you know a little bit about this market of solar cells. It's basically like silicon-based solar cells. Everywhere is just silicon-based solar cells, right? But we do have like better alternatives for that. But the problem is like to implement that in an industrial level. It's just like not very economic. So that's why people don't do it. So you kind of have to you have to push the theory, let's say, but you also have to push like the actual making the device in real life. Yeah.
And when thinking about solar cells or really anything that's used for optoelectronics, and I'll let you correct me if I'm wrong, optoelectronics meaning converting light to electricity or electricity to light?
Yeah.
Yeah, so when making materials for optoelectronics, what are the things that you want the material to do really well?
Yeah, so most of the optoelectronic applications, they have kind of like these properties that we would like them to have in common. Like all of them have the same types of properties, and then they diverge a little bit at some point. Well, like for example, if you think about a solar cell, you want your material to have like a nice band gap, like an electronic band gap, so you can cover the most, like let's say, the biggest part of the solar spectrum, because you don't want to be losing like sun energy. You want to be able to collect it.
Yeah, you want to collect like as much of that electromagnetic spectrum as possible,
Yeah,
much of that visible light
exactly.
as
So
possible.
if you look at the plot of solar spectrum, something like this, so you want to have your band gap close to this maximum thing, so you have like maximum absorption. Yeah. So like in fact, like no material can capture the whole solar spectrum, right? That's why you're never gonna have like a solar cell that's 100% efficient. There are some limitations, and it's usually like around 33%.
Yeah, that's the oh man.
It's called a Schottky quasi-limit.
There we go. Yeah.
Yeah, it's the most simple, let's say, criteria that we have for like efficiency of solar cells. There are other ones as well.
What exactly is meant by like 30% efficiency?
Yeah, it's just because at some point, you have to have your band gap good enough to start absorbing like all this infrared region of your solar spectrum. But if your band gap is too big, you also start to generate a lot of like this thing that we call hot carriers. You have like a lot of carriers being excited, and this actually drops your efficiency instead of boosting it, because you start like converting a little bit of this energy in how do you say, heat.
Yeah.
Yeah, and you don't want that, right? You want
Yeah.
to convert it to electricity, not heat. Yeah, so like there's this let's say sweet spot of the band gap, and that's exactly what the guys did back in the day.
So when you say like 30% efficiency in a solar panel, that would mean that in the amount of light energy that's hitting it, 30% of that is getting converted into electricity that we can use.
Yeah, it's a relationship between like let's say the power that's being incident and then power that's being generated. Yeah.
Yeah, I was a little bit confused on what exactly you meant by efficiency.
Of course, this is like it's a simplistic criteria assuming just one material, right? Like if you take, for example, silicon or whatever, like 33% would be the best thing that we could have for any single material. But you can think about like starting doing like sandwiches between these materials. For example, you can put silicon, you can put a perovskite, you can put something else, and then each material starts to absorb like a different part of the spectrum. You know, you lose a bit of energy in this process, but still, like the whole device performs much better than 33%. So you can surpass that. But
yeah, they have these like these tandem cells.
Yeah, exactly.
So they'll put like silica on top of the perovskite, and then other stuff that I do not know because I'm not an engineer. But they'll layer other stuff and help with the conductivity and things like that. I was wondering what your opinion on the tandem cells were.
I mean, I think for at least for now, it's the only pathway that we have to, like, make solar cells better. You know, because since we don't know how to surpass the Schottky quasi-limit problem, like you have to resort to start combining different things, either doing tandem cells or whatever. So yeah, I think that's the only thing that we can do for now. But, they're for sure dominating the market now, right? Like if you look at silicon, it has been growing up quite a lot in efficiency in the past couple of years, and perovskites kind of like had this big jump over silicon. So they're actually better than silicon. Then you mix both and you get something that's even better, So you can start playing around.
Yeah. Yeah, because I know that there's been a couple studies done relatively recently that have exceeded that, I guess, pre-noted limitation, the quasi limitation. There was something done in China, and I think
Limit, like a spectral limit.
no. I'm sorry, just like the efficiency limitation.
Yeah.
That like 33%. I think they hit like, 34.9 or something.
Yeah, for sure. And there's even there's things that are even better than like perovskites and let's say silicon, but like usually people don't use like on Earth. It's this type of stuff that we put like, for example, on spacecrafts. Yeah, it's just too expensive to produce, but they're very good. So like when it's for these very specific high-level applications, they build it.
Is it expensive because it's rare, or is it really hard to make? Or
it's very hard to make, and some of them are very rare. Like for example, the best ones, to my knowledge, are like some solar cells based on gallium arsenide, which is a material that is very well known, but super hard to make, especially like a very high quality single crystals of gallium arsenide. So that's a big of a problem if you want to scale these things,
Yeah, and I wonder how the ease of manufacturing of perovskites compares to silica. I know that like with silica, everything has to be completely perfect, and if you get like a scratch or like if you get like a misalignment, then the entire cell is ruined. But with perovskite, all you need is to like lay out a thin sheet, so it can be actually like a lot thinner, and like you don't need as much of like a careful manufacture process.
Yeah, sort of. I think both of them are fairly easy to make. Let's say perovskites, people can do even like with spin coating, which is basically like a spinning blade. You just drop some liquids on top, and like this thing spinning and heating, like a crystallize the perovskites on top. So it can be very simple to make, but yeah. Okay, can you repeat? Sorry, your question.
No,
Just
yeah, you're
I
good.
forgot the point.
Just like, how does the ease of manufacturing compare to
Oh
silica?
yeah. So like they're very similar to make. I think the main thing is that silicon is already on the market for many years. So you have, I'd say it's very hard for you to compete with something that's already very abundant. So much abundant that you cannot even use everything that you're producing. So yeah, so that's, I think, is one of the main challenges towards like taking perovskites and replacing silicon with them. I think that's why people are trying to mix them instead.
Yeah, that was a big problem with electric cars, right? Like there just wasn't the infrastructure necessary to have like charging stations and things that the technology needed in order to like survive and take off. While we're talking about perovskites, could you talk to me about what a perovskite is exactly?
Yeah. So, okay. So, like, historically speaking, perovskite is the name that people gave to this calcium titanite material, which is basically calcium, titanium, or like oxygen 3. Yeah. So this was found like in Russia many years ago, 1839, by a guy, and they named it like after this Levi Perovsky that was a kind of funding the expedition basically. So that's why it's called the perovskite. But it's, if you think about it, it's kind of like an octahedra, right? So you have like a one on the top and one on the bottom. It's like a diamond if you think about it. Yeah. So each corner of this diamond, you have your, in this case, oxygen, in the case of calcium titanite. On the middle of on the center of the octahedra, you have another atom, which is usually like the metal species, in this case, titanium. And these octahedra, they're kind of connected to each other. So like in each corner of this octahedra, you connect a nearby octahedra. So they form this like a three-dimensional, let's say, network of corner sharing octahedra. Yeah, it's something quite interesting like to look at. And you see the calciums, they are kind of trapped within these octahedral cages. I don't know if you can use visual recourses for the podcast, but
I'll put like I'll put that in like a little short clip edit, and then
yeah. So like this is kind of like how they first appeared with calcium titanite, which is an oxide. So oxide perovskites, they were discovered first, but eventually people found out that there's like a bunch of materials in nature that actually exhibits the very same type of crystal lattice that calcium titanite. So nowadays we basically call all of them perovskites. Yeah.
Yeah. Funnily enough, so I had an interview right before this, and the researchers that I had on way back in the day did some mantle modeling and modeling of the lower mantle, and there's the lower mantle's filled with perovskites, and it's basically like I think it's the same elements. So olivine is a rock that's like super abundant in the mantle, and somewhat abundant on Earth's crust. It's kind of hard to come by. It depends on the type of rock that you find, but way more abundant in the mantle. And it's the same combinations of elements. So it's like there's two species. It's like iron and magnesium, and then oh man, I forget the full. I think it's iron and magnesium, silica, and then oxygen. So oxygen would be that kind of non-metal, like I don't want to say gas, but like non-metal component in that cage, and then you would have the magnesium or iron as like that metal that you're talking about, and then silica being like the rest of that structure that kind of holds the thing together.
It's probably what we call a double perovskites. Like usually when you have like a 4 atoms instead of 3, usually you have 2 different species occupying this center of the octahedron. So you can have, for example, I don't know, silver here, iron here, and then silver, iron, you know, like it repeats like this.
Oh,
so we call
really
this
cool.
a double perovskites.
Yeah.
They exist, yeah.
Yeah, that exists naturally. You'll find like rocks. So there's like different species of different minerals that, like olivine, for example. There's like iron-rich and magnesium-rich olivine. And so if you have like a rock of olivine, you might have like a pretty good mixture of like iron or magnesium, but then it might be more iron, more magnesium dominated. Yeah.
Yeah, it was this point that you mentioned was kind of interesting because perovskites, they are super abundant on Earth, but not really the perovskites that we want for solar cells. Like you can get very good solar like perovskites, oxide perovskites for like XRD detectors and things like that. But for solar cells, you usually want the halide perovskites, like the ones that are not based on oxygen, but like on halides, like chlorine, bromine, iodine, fluorine, so on and so on. So because these ones, they tend to have like a good band gap, you know, like in this region that we want. And the problem is that they are much more unstable as well. So that's also one of the challenges to put them on the market is because it's very hard to make them like stable over like several hours. Or, you know, if you want to make a solar cell, you want it to be stable for like thousands and thousands of hours.
What do you mean by band gap?
Yeah, so like band, for example, you think about okay, you know what's an isolator and what's a semiconductor, and what's a metal. So like you have isolator, semiconductor in the middle, and a metal. Insulator, they have like this very big band gap. Let's say if you think about the energy levels of your electrons on your valence bands, they are here, and there are some like imaginary, if you want, like conduction states here. And what you need is to provide a certain energy in order to excite this electron to these bands that are free. So like they're not occupied. So like the electron, this energy that you need to give is what we call a band gap. In an insulator, this band gap is very big. In a semiconductor, it's fairly small, usually like in the visible range. Yeah, and then like in metal, you have this cross of the energy levels connecting like the valence and the conduction band. So you don't have a band gap. You see, they are always free carriers there.
Ah, gotcha. And so when you excite that electron to the higher energy level, does that mean that it's able to travel through the substance like in a metal, or does it stay in that?
It will. So that's a good point because like it will stay there for a while. Yeah. So and then eventually it will recombine. So it's what we call a recombination rate, or you can also like take the inverse of these things and you can think about this as a carrier lifetime. Yeah. So like once you excite your carrier, it will stay there. And if you want to have a good solar cell, you have to be able to collect this carrier before it recombines, because otherwise you're going to emit light and you're not going to generate electricity. So you don't want them to combine. Yeah. So.
Yeah. And that emission of light is what's happening. I mean, it's the reason why lava glows. It's the reason why your stovetop glows when it gets hot. Yeah. It's like, that's cool. Yeah. I was always a bit confused on the actual like quantum physics of how you almost like store a photon whenever, or like you store the energy of that photon whenever you excite the electron to a higher energy state. And then is it like when the electron goes back down, you emit a photon and that's why it's like glowing, or?
Yeah, exactly. So like you excite the electron. Once the electron recombines, it has to emit the difference in energy to conserve energy, right? So you always have to be conserving energy. So this energy is the visible light that you see.
So photons will like, is it right to say that they'll like pop in and out of existence, or they're kind of converted into energy and
Yeah,
then converted back into like a physical particle that we can see?
yeah. So the way that I like to see these things is that like when you have okay, well, your electrons in your material, they kind of form these dipoles. Okay, so like these dipoles, they form electric fields, right? So electric fields, they can store energy, right? So when for example, a photon comes, it's just like an electromagnetic wave. So like this electromagnetic wave interacts with your dipole, and this energy is stored in the electric field formed by your electrons. So you see, so like this energy is not like appearing or disappearing, but it's like just being added to like say for the dipole moment of your electron.
Yeah.
So this is actually what you calculate when you want to, for example, do prediction for like absorption coefficients. You need to calculate this dipole strength. You know.
It reminds me of like a complex like spring system. So if like something's oscillating and it's oscillating in some weird way, and then you like perturb the system a little bit, you're gonna add that energy to the system, and then in this case it would just like kind of, maybe you have like your energy system here that's going like this, and then you have like a spring here and a spring here, so you like perturb that spring, and then it travels through this energy system and then exits through that spring.
Yeah, that's pretty much what happens, I believe. Yes.
Yeah.
Yeah, like it can be even much more complicated than that, because when we're saying, okay, light comes, excites an electron, it recombines and emits light. This is just for like what we call direct band gap materials. It's just like when you don't have to provide momentum in order to have the transition. You just provide energy, which is what the photon does. It doesn't provide momentum to the electrons, just energy. But you can have like electronic transitions to other conduction states that are in a different momentum. Right. So in order to like these transitions to happen, you have to have interactions of the carriers with the lattice, like with the crystal lattice. These ions, they are vibrating, and your electrons are trying to move around, and they interact. So like this interaction is what kind of like provides the extra momentum. And this is actually one of the things that we do on our group. Yeah. It's like an example of electron-phonon interaction problem.
Yeah, I was about to say that's what you're describing a phonon, right?
Yeah, it's a phonon-assisted absorption.
And phonons are categorized as quasi-particles.
Yeah.
So something I was so confused by, and I was hoping you could explain to me, is how does a phonon behave like a particle but is not a particle, or I don't want to say a wave, but like it's not a particle but it behaves like a particle. Can you explain that?
It's very hard to visualize because it doesn't exist, right? It's just a vibration that's moving around. And if you solve your Schrödinger equation, like the phonon is just like one of these quantum index that you have. But like I think like in order to understand like what's a quasi-particle, all of them have like the same. How can I explain? Like the same fundaments. Like they don't exist, but objects behave as they were particles. For example, you have a lattice, right? Your lattice is completely neutral, right? There's no charges. Like okay, your charges are balanced, and your lattice is neutral. You put a charge in the middle, like a positive or a negative, it doesn't matter. So like this charge will polarize your environment, right? So like if you have if your charge is negative, it will like attract positive charges, and it will repel negative charges. So you're gonna have like your particle and a small, let's say, polarization cloud around your particle, right? So like this thing that is the polarization cloud plus your electron actually behaves as a particle. So yeah, so this is something that we call a quasi-particle in band structure theory. So these things exist. They are not like a particles itself, but like they kind of collective behave as a particle. Phonons do the same thing.
Is it, are there like individual sections? So there's a couple atoms that are vibrating together in a certain way that you would classify that as a phonon, or do you classify it over like a broader, large-scale material sense? So like the entire solar cell, or?
It usually depends on like how many degrees of freedom you have in your system. Because, for example, if you have just one atom, right, like just one atom in space, you can have 3 degrees of freedom. You can go like this direction, or this direction. So these translations is what we call acoustic modes, if you want. Yeah. And then you can have, for example, systems where you have two particles, and then you can have, again, like these rigid translations of your systems, but you can also have things like this, things like this. So these are your optical modes. So usually you have like let's say 3n, where n is the number of particles for like you have 3 acoustic modes and 3n minus 1 optical modes.
Okay.
For depends on the number of particles that you have. It's just because it's these combinations of how you can do this with different like a certain number of particles.
It reminds me exactly of a spring system.
Yeah, it's exactly what it is. Phonons are exactly like basically spring systems. Yeah.
That's really, really cool. I was literally just talking to Jay over here about how like or the universe kind of mimics itself on the micro and the macro, or like the macro imitates the micro, and that is perfect example.
Yeah,
like
I think in a
perfect.
fundamental level, everything are like oscillators, you know, quantum oscillators.
I saw some kind of quote where it was, I have it written down somewhere, but basically like atoms are like springs that all kind of behaved or like oscillate together, and so how exactly does a phonon interact with, let's say, so you're saying it behaves kind of like a particle and it has kind of particle-like behavior. So how is that going to interact with maybe an electron traveling through the material?
Yeah, okay. I actually had to answer this question before. So like I guess you can imagine like your electron as being, okay, it's a body, right? Yeah. So I don't know, you put a body in the middle of this table and you splash water, right? Like this water is just like a wave and it's going to scatter this electron around. That's exactly what happens with phonons, you know. Like your material is vibrating, it's oscillating. You can imagine your material doing something like this. The electrons are trying to travel inside, you know. And this like oscillation just scatters your electron around. So it makes gain momentum, it makes you lose momentum. So that's what makes you like being able to, I mean, electron phonon coupling is like the origin of many things in physics, like transport, phonon system optical absorption, superconductivity, polarons, excitonic polarons, and like the list just goes, you know. Yeah.
So it's like like if you think of the whole system as like you said, like it's like the surface of the ocean or like surface of a pond. Your electron is like a beach ball that you're trying to get from point A to point B.
Yeah.
And then the different waves and the different currents are like your phonon that are kind of like bouncing the ball from place to place.
Exactly. Yeah. So it's much more complicated than one single wave. It's just a bunch of waves interact in a very complicated manner.
Yeah, and it's all three-dimensional too.
Yeah.
When you really get down to it.
Of course, this is just like a very simplistic view because the electron is not like a point, but the principle is the same.
I'm sure those computer models get really complicated really fast
for
when you
sure,
start
for
adding
sure.
geometry.
For sure. Yeah. Luckily, people did many things before we started working electron phonon, or like all the basis was done, which is the DFT, right? This functional theory.
So what about excitons?
Yeah.
What are those exactly? So they're also quasi-particles, but...
Yeah, exactly. So we were talking before about these optical excitations. So you have your electron being like excited to your conduction state, right? So when you do that, like you leave a hole in your valence band. So like this hole is also not a particle, right? Like it doesn't physically, it's not a fundamental particle, but it's like a positive charge, which is exactly equivalent to your electron.
Yeah,
right?
The vacancy is equal to your actual particle.
Exactly. So your electron is excited, it leaves one spot free. So like this spot is like a particle as well. We call it a hole, right? So when this electron recombines with this hole, it generates like light, as we were talking about, right? But some materials, they have like this very, let's say, evident excitonic effects, where like you excite your electron, and these two particles, they are very strongly coupled with each other. So it's not all materials, like all materials have excitons, but like some of them have very localized excitons. And then usually depends on usually depends on the dimensionality of our material, to be honest. Like the lower dimensional materials, they tend to have larger, like let's say, binding energies for your excitons. They tend to be more coupled together, just because they don't have where to go.
Do you mean like a octahedral material versus like a maybe a tetrahedral lattice, or
Yeah, if you think about the perovskite that we were talking, and just one octahedra, if you have just one octahedra in vacuum, your carriers, they don't have much like where to go, you know? Like, so the excitons will be very bounded, like the electron hole pair will be very bounded. But if you connect these octahedras and form a perovskites, now they have like a bunch of places to travel. Yeah. So they will tend to have like a smaller coupling.
and do those kind of excitons, do they form and kind of dissipate in some kind of like oscillatory pattern that you can predict, or any kind of pattern that you can predict?
Sort of, yeah. So what happens is that they usually, for example, if your band gap is like this within DFT, right, like this, let's say, when you have like a very strong exciton effects, when you recombine your electrons, they will actually tend to recombine from a lower energy state. Yeah. So for example, if this was, I don't know, 1 EV, but the electron hole strength is very strong, let's say, this can recombine with like let's say an energy of 0.8 EV instead of 1. So like they can actually push your band gap down. So that's why they are so interesting for LEDs, for example. They are behind most of the optical emissions that we see in LEDs.
So are you saying that like the amount of energy between the energy levels decreases, or like that 0.2 electron volts went somewhere else or did something else or got like incorporated into a different atomic system?
Yeah, okay. Now we have to go back to the quasi-particle vision that we were talking before, right? Because if you have an electron and you form this polarization cloud, the same thing happens with a hole, right? But the thing is, like, if you have just an electron and a hole and they are on vacuum, there's nothing else, like they interact with a certain strength. If they have like this polarization cloud around them, they see each other much weaker. Like the interaction is much weaker between them because there's like this whole polarization cloud of like charges that they are screening, as we say, like the interaction between them. So like this it changes like in the effective screening is basically what gives this difference in energy. Yeah.
And I know I'm vaguely familiar with all of Schrödinger stuff and how electrons will appear and reappear out of existence. So when you have an energy level in the electron cloud, it's basically saying that there's a very likely chance that this electron will show up in this area given the amount of energy that it has. So when you excite an electron to a higher valence state, so basically a higher energy level, is there still a probability that it'll show up at the lower energy level?
Yeah, for sure. Like quantum mechanics is pretty much probabilistic, right? Like there's certain things that we can calculate like exactly, but if you talk about electron wave functions, these things are just like blobs of charge density because you don't know where your electron is. So you kind of have like a probability of doing pretty much any transition in your band structure. Like say if you have like a whole set of valence bands and a whole set of conduction bands, all these transitions, they are possible, but like, they start to become less and less probable. You see, like even like phono assisted transitions, they are already much harder to make because you need both energy and momentum conservations to make. Yeah. So they are So like usually the direct dominates. Usually it's not the case for all materials. Silicon just works because of electron phonon interactions. Otherwise it would be pretty much transparent to sunlight. Yeah.
Yeah, so these like almost like outlier cases where you just get that lucky chance where an electron goes down to a lower valence level for a second, then goes back up to where it should be, happens so infrequently that it really doesn't change the overall behavior of the material. It's like, technically speaking, if I like hit my hand against the table for an infinite amount of time, there's like a chance that my hand could phase through the table, but it's like never gonna happen.
Yeah, it might take a very long time. Yeah.
Yeah. So how do excitons, so this kind of like quasi-particle of this attraction between your electron in the higher valence state and then the vacancy that it leaves in the lower energy state, and then phonons, the kind of shaking of these atoms and these systems within your crystal lattice, how do they interact with each other?
Oh yeah, so that's a good question, and it's something that we were investigating just very recently. From a computational point of view, like being able to do this type of calculations of excitons coupling with phonons, it's something that happened like last year, pretty much.
Oh wow.
Yeah, I mean there was a paper a couple years ago that people did something quite similar, but last year people in our group they developed like a theory exactly to do that. So it's an ab initio methodology, yes.
And circling back to Perovskite, what about Perovskite now, or I guess now with like hopefully a decent understanding, if you're listening, of what phonons are and excitons and these different particle and quasi-particle systems that are dictating the different properties of perovskite. What about perovskite, I guess, in regard to those systems makes it good for optoelectric applications?
Yeah. So okay. So we can circle back indeed. As I said, the band gap is good. So that's the first point. So the second point that this three-dimensional perovskites that I was talking about, right? They have small external binding energies because they're like three-dimensional materials, so on. So we don't have these problems with excitons, which is something that we don't want to have for solar cells. Excitons are good for light emissions, but not for solar cells, just because you're going to lose a bunch of carriers that recombine, and it should not, you know. So you want to have also very good transport. You want to be able to extract your charge carriers before they recombine, right? So this is also coming from electron-phonon interactions. So you have to have good charge carrier mobilities for both electrons and both holes. Because sometimes you can have these situations where your electrons move very fast and your electrons and your holes are very slow. So if one is very fast and the other one is very slow, you cannot produce current effectively, you know, right? You have to push both of them at the same time in your circuit.
Okay.
Yeah. So I think these three are kind of like the pillars of a good solar cell, and perovskites have all these attributes. So that's why they're so good.
And does perovskite have anything that silica doesn't in regard to this stuff?
Well, it has first the direct band gap. Silicon is indirect band gap. Okay. So we can define a direct and indirect band gap. Yeah. We are talking about a direct band gap is just when you just have to give energy, right? You don't have to provide momentum, right? But some materials they have, for example, you can imagine that you have a band like this and then a band like this. So instead of exciting to this higher energy band, he will prefer to go to the one that's a little bit lower in energy, you know, because you always try to minimize the energy, right? There's no reason for your electron to be excited up there. So it goes to the bottom of your conduction band. And this is when you have to provide momentum to do these transitions is what we call an indirect band gap. Okay, so I think one of the main differences is also related to what you were talking before, is that the solar cells based on silicon, they are very thick, right? So they're much thicker than perovskite solar cells, which are very, very thin. And the reason for that is because silicon is indirect. So if you want to be able to capture all these, let's say, phono-assisted transitions, you have to make your material very thick, so you can have a lot of time to extract these carriers and generate current. Otherwise, they would just recombine very quickly. So you have to give them time to be, in fact, absorb it. You see what I mean? So in perovskites, this is not the case, right? Since they are direct, you can make them very thin. You save a lot of money, a lot of material.
Yeah. So when talking about giving momentum to the system, or so direct versus indirect, is the photon itself, when it kind of, maybe not crashes is the right word, but kind of when it makes contact with that atom, is that the source of momentum? Kind of the same way I would throw something at the wall?
Yeah, it's a bit complicated because there's nothing really shocking with each other, but it's just two waves interacting with each other if you want. You try to put a wave on this side, a wave on this side, they will collide and something will happen. That's what happens in reality as well. Yeah.
Is there any kind of resonance frequency of light that interacts with a phonon in a way that, because when thinking about acoustic waves or waves in a spring system, there's if I force the system at a certain frequency, then I'm going to reach resonance, and then this whole system is going to like grow with time, and it might exponentially grow. And then there's also frequencies where I can hit it, and then like the frequency at which I'm forcing the system like completely cancels out the frequency that it's already oscillating at. Do you find similar things with light and phonons and different things?
Yeah, for sure. For phonons, that's why I think that's basically what people do in Raman experiments, right? Like you try to excite some specific phonon modes. Some of them are like a Raman active, as we say. Some of them are not. Some of them are infrared active. But like at the point that you excite specific phonon modes in your system, and they like appears in a plot like a sharp peaks. Mm-hmm. So you can definitely do that. Yeah. So this tells you a lot, you know, about like the types of vibrations you have, like how they are vibrating. Like if your frequencies of your like acoustic optical modes are very high, this might lead to a lot of scattering in polar materials, for example, like that have a lot of these like intern dipoles and things like that. So Raman can be very useful for that, and also theory, because we can also compute these things.
When you say scattering, do you mean scattering of light, scattering of energy?
Yeah, it's a scattering of like an electron, basically. Like this electron is usually scattered by like the lattice vibrations, right? The phonons. Yeah.
Okay.
So it's basically this wave shocking with the electron and scattering somewhere else.
Okay. So ideally, you would want the electron to travel from point A to point B. So, you know, wherever you have light hitting the solar cell and you're starting to generate some energy, or usable energy, you want that electron to be able to go from point A, or I guess the electron itself isn't traveling. It's like the energy of that electron that's traveling through the substance. So you want that energy to be able to go from point A to point B with as little impact from the surroundings as possible.
Ideally, yes.
Okay. And then what about LEDs? So we've been kind of talking about Perovskite and these systems in regard to absorbing light, right? And LED seems like it would be emitting light. So why is it good at absorbing and also emitting?
Yeah, there's some people that say that a good solar cell is also a good LED, just because like you want to be able to absorb your electrons in both cases, right? So you want that for both solar cells and also for LEDs, but you also want to be able to extract these electrons fast. All these properties that you have for solar cells, you also want to have for LEDs. So I mean, usually they tend to be like a good in both because of that. You know, the main difference is that like usually, for example, if you are focusing on LEDs, you might focus on lower dimensional material, so you can have this very bounded exciton states that we're talking about. Mm-hmm. This allows you to like tune where your emission is, and so on. So you can have like green LEDs, blue LEDs, red LEDs, and so on.
Okay. And then let's talk about the different, I guess, geometries of perovskites themselves. I know you were talking about it earlier, but there's like n=1 and n=2, and then you can like really get into the weeds of like 3D. What are the differences between those three?
Yeah, there's perovskites nowadays are pretty much azul. There are so many types, you know, things that we would not call perovskites, they are called perovskites, just because you can make some connections between the properties of both systems, you know. But you can have like this 3D perovskites that we were talking about, which is basically this network of octahedras in 3 dimensions, but you can have them in 2 dimensions, right? So like these are the layered materials that you're talking about, n=1, n=2. Mm-hmm. So usually like when you say n=1, you have like a 1 perovskite layer. When you say n=2, you have like 2 perovskites layers and then like vacuum. Mm-hmm. It's not like, in reality, it's not, of course, it's vacuum. Usually people put like organic molecules inside these empty spaces, right? Yeah. So you have like a perovskite, organic molecule, perovskite, organic molecule, and so on. So this forms like a 2D system. Okay. Yeah, so like one of the advantages of these things, for example, layered perovskites, is that since you have organics, you can think about, for example, putting hydrophobic organic cations inside the perovskites. So if they are hydrophobic, like water will not go inside. And this is one of the main sources of like the stability problems of perovskites, is moisture. Like water enters inside, and messes up everything. So if you have like these hydrophobic organic cations, water will not penetrate so easily. So they tend to be more stable, but at the same time they tend to be not as good as 3D. Because they are 2D, so you have like Excitons, and you have a bunch of other effects coming on as well. Also some electron phonon effects as well.
Yeah. Yeah, because or at least from the research that I've done, perovskites are like promising, but and they're promising in a lab and they're promising in models, but when you put them outside into like real atmospheric, real life conditions, then they wear down really, really easily.
Yeah, I mean, people have been putting a lot of work into that in the past couple of years. Nowadays, it's much, much better than it was before. Like, we can definitely get like some thousands of hours, which is good.
Oh, really?
Yeah, it's very good. So actually, I think like last year, there's a startup that started producing silicon perovskite solar cells, like heterostructure solar cells.
Yeah, those like tandem.
Yeah, and I think it's like the first time that someone tries to commercialize perovskites, which is quite interesting. But this is a startup. As far as I know, there are no like a big companies doing it for now. Yeah, although like I think perovskites will be much more interesting for the LED part for sure. Like if you look at LG, like the company, television LG. So like I think they put out 5 or 6 patents on perovskites in the past 2-3 years or something. And there's also Samsung that did the same. So like people are starting to produce probably like PLED TVs, which is like perovskite LEDs.
That's really cool.
Yeah, it's pretty cool. Samsung, for a fact, they already start producing some XRD detectors, perovskite based, which is cool. And I think LG is based basically on the TVs.
Yeah, they come out, or I don't know if they're using perovskite, but there's like some catchy commercial name they're using for that. It's like quantum vision or like quantum pixel or something.
Yeah.
So if we use perovskite, or if we're able to like apply the technology to LEDs and TV screens, would that increase the amount of resolution that we'd be able to do, or maybe the energy efficiency of?
It's a bit of both. I think if people can make it work, it will be a bit cheaper than maybe some of the technologies. Not all of them, but some of them. But I think one of the main advantages is that, the color purity of perovskites is very good. So there's this international scale of how pure is the emission of a certain LED, and perovskites tend to perform very well. Also for LEDs such as blue LEDs, which are super hard to make. It took years and years for people to be able to make a blue LED, and perovskites are very good on that.
Yeah. Interesting.
Yeah.
So, what do you mean by the kind of like richness of an LED, or like I guess like the richness of the color, or like?
Yeah, maybe you already saw at some point. There's this. It's called CIE plot. It's like a chart like this. Looks like a small blob with a rainbow. It's basically a bunch of colors. Oh, yeah. Yeah, and on this plot you have basically all the colors. Yeah. And there are some standards. For example, if you take a NTSC, which is TV, and you also have like a 4K, 8K. So they're all sitting in different points of this plot. Yeah. So these are the standard, let's say, for commercialization. And you want your material to have the emission, if you take the color of your emission, to be as close as possible to those points on the plot. So that's basically what it is. You just look at the color of your material, of your LED, and you take the respective color on the plot.
Mm-hmm. Okay, so if you were looking at a rainbow, it'd be like the red LED in your TV will give you red in a certain range of that red part of the visible light spectrum.
Yeah.
And you want it to be as close to perfect red as possible, and lower that kind of uncertainty of what it'll give you.
Yeah, if you look at, for example, at emission measurements, usually what you have is you have a plot, and then you have usually what you want is a very sharp peak. So let's say your x-axis is the energy. So you have a very sharp emission in a certain energy, right? Most of the times what happens is you have something that's quite broad. So instead of having something that's very, very green, it's a little bit of green mixed with white. So it's dilute the color a little bit, And this can happen because of like defects in your material, a bunch of things. Yeah, so like these things people try to reduce.
Do you think that the lifespan of LEDs will increase with perovskite?
Yeah, that's a good question. I'm not sure about the lifespan. I'm not sure if people really did that. It's the same. It's true for perovskites because it's very hard for you to tell. Yeah, my solar cell will last like 10 years because we didn't have like 10 years with the device to test it. You know, so it's a bit of approximative. But they should be very stable, at least as stable as the current technologies for sure.
Okay. And between, I mean, you've been talking a lot about like how many different perovskites people will bring to the table. Are there any differences in kind of species? Species is the right word, right? Like there'll be like a magnesium iron dominated,
Yeah.
or like a cesium bromine. Is there a difference between species in, let's say, the more emission side of things, so like LEDs versus more absorption, which is like solar panels and things like that?
Yeah, for sure. Like all perovskites, they are different from each other. You can always trace like their properties back to something in common, but like the band gaps can be very different. Like exciton binding energies can be very different. Transport can be very different. So usually the best ones that we have right now are these like they are kind of like you have this set of organic compounds and like some inorganic compounds that are like your spacers is what goes in the middle of your octahedral cages, like the calcium that I was talking before, you know. Yeah, so you can have like a combination of a bunch of things, and then you can have lead, and usually you have like a halogen. So like this kind of combination gives you the band gap where you want. So if you change, for example, from iodine, which is a halogen, to bromine, which is also halogen, your band gap will increase. So like if you change for chlorine, your band gap will increase again. So yeah, the larger your the mass of your halide is, the smaller your band gap will be. This is not like a, let's say, a universal trend, but that happens just because of the physics of the materials, like a spin-orbit interaction thing.
Are you familiar with clathrates at all?
With?
Clathrates or
Sure.
hydrates? So
Oh yeah.
it seems like you are, but basically it's when you form almost like a crystal lattice cage around, like, usually it'll be a hydrocarbon, so like methane. You'll form, so there'll be like methane mixed with water, and the water will freeze around the methane. And so it reminds me a little bit of a perovskite, where you have like this like negatively charged non-metal like in the center, and then you have a cage of water is not, it would be entirely non-metal elements, and I think the hydrogen that you have around that oxygen is going to behave differently than like a cesium atom would, because there's just so many different, or there's only one electron in hydrogen, right?
Yeah, exactly.
But it does remind me of perovskites a little bit in the way that crystal lattice would be set up. And I am curious if there's any like conductive properties that are different in that compared to...
That's a good question.
Yeah.
I don't know. I have no idea. I never
Yeah.
work with like this type of materials. But what I can tell is that they're probably going to be very different. Like even within the perovskites that we call perovskites, they're already very different, you know.
They would have like no... I don't want to say no, because like I feel like working in science, you learn pretty quickly not to work in absolutes.
Yeah.
But it would be very difficult to find a way to find a useful application for them, because like they're so hard to maintain when you don't have the right temperature or pressure, because they only form at really low, like sub-zero temperatures.
Oh yeah, so that's a big deal. Yeah.
There has to be a ton of pressure as well.
Yeah, it's a huge problem.
Yeah. It'd be one of those. I guess it's just a wacky curiosity. Maybe in space.
Yeah, I mean, it could be, maybe someone call it a perovskite. As I said, like nowadays there's a bunch of complicated terminologies of perovskites. For example, I worked with one maybe 1 or 2 years ago, which is basically a perovskite octahedra.
Mm-hmm.
But instead of having like the nearby octahedra being connected, you have like an empty space, like it's a vacancy. So you have like a
Oh.
octahedra, vacancy, octahedra, vacancy, octahedra. So it's like it's almost, if you look at the material, it's almost like some isolated octahedras that are kind of close to each other. So they see each other, they interact, like electronics speaking a little bit, but they are not connected. So if you look at the material, it doesn't look like a perovskite at all. But you can trace it as a perovskite because you can imagine the vacancy as being like a double perovskite. So it's like a metal and a vacancy instead of like two different metals as we were discussing before.
How does the phonons in a material like that differ from like a normal 3D
Yeah,
perovskite?
it's very hard to track like exactly how they differentiate. For sure, like the frequencies are very different. Like in this case of like, for example, vacancy or perovskite, since they are not connected, the octahedras are much more like dangling, like they are moving much more because there's nothing like to constrain them of moving. So like the frequencies changes quite a lot. Yeah.
Yeah, like there's no um like if I'm in the corner of that space over there, that would be like a tiny packed,
Exactly. Yes.
like 3D normal perovskite. And so if I bounce against the wall, like I'm gonna bounce back, and then like there's not a lot of room for me to go. But if I'm just connected at like my top and my bottom, and then my sides, and I'm just like,
Yeah. Exactly.
Yeah.
Yeah. That's pretty much what happens. Yeah.
that's really really cool.
Yeah.
Do you mind if we go to the bathroom real quick?
Yeah. Of course.
They're really cool looking. I don't know how practical they actually are.
They're okay.
Yeah. Because they have this, they have like a stainless steel body or something,
Yeah.
but they don't have the right coating on it, and you have to pay extra to get the coating, and you have to get it reapplied pretty regularly, right?
Every 6 to 12 months or something like that.
Damn.
It's just stupid that I need to put automatic down payments on my car and then have to like update my car and then
Yeah.
having to put a new ceramic coating, or not even a ceramic coat, but just a new coating on my car that should have been on there.
I think people were like observing rust on their cars like the second day they got them, or like
Yeah, I heard about it. It's
Yeah.
pretty bad.
there's a guy at my apartment complex that I don't think he lives there, but I think his girlfriend does or something, and he picks her up in the Cybertruck. So I saw it up close, and I wanted to like run up to him and be like, "Hey, like, do you like it? Like, is it actually a good car?"
I will say it is because he bought it.
Yeah,
Yeah.
true. He has to justify his.
Exactly.
I don't even know how much are those. Like $80,000.
Very expensive. I don't know.
Yeah. Could you tell me what a density of state is?
Yeah, it's basically like the amount of states that you have per unit of energy. So, for example, you have one atom. You might have, let's say, one band at close to 1 eV. If you have two atoms, you might have two bands close to 1 eV. So, like in this case, if you look at relatively speaking, you have more states within the same energy window. So, like this is pretty much how we define the density of states. You can calculate all these states from quantum mechanics, like Schrödinger equation, and then you calculate this density over your volume of space.
Okay. So is that like a function of almost like how many electrons that particular atom has? So if I just isolated the atom itself.
Yeah. It's a function of like how many atoms you have, like where the energy levels are sitting, how dispersive your bands are. Like it's a bunch of things. Yes.
And for so let's say I have a smaller metal that has less electrons than a larger metal. Is the amount of energy to go from, let's say, I don't want to say I think they taught it me in chemistry, but let's say just like my second lowest valence, or not valent, but like my second lowest energy level to my third lowest energy level. So like going from 2 to 3. Does that take more or less energy than going, let's say, from like 5 to 6?
Not. I mean, it depends how spaced your bands are. But if you're talking about a metal and your bands are like all crossing the
Yeah.
band gap, there's no really like energy cost for
Okay.
it, because like
Yeah.
any energy that you give, like you're already gonna excite your carrier to like a conduction band. But like if you're talking about like an isolator, it really depends on like the spacing between these bands, because one band might be coming from one atom, for example, p orbital of silicon. The other band might be coming from s orbital of silver or whatever.
Oh, okay,
You
okay.
see, so like your bands, they are formed.
Yeah.
You're not like most of the times they are formed by a combination of orbitals from all the species, not like just one specific.
Is it so those excited electrons are shared between, so like if I had a cesium, titanium, and bromine perovskite, it those like excited electrons would be shared between that cesium and titanium?
It depends. Like in perovskites, for example, like you have like cesium, titanium, bromine perovskites. Yeah. In this case, cesium usually doesn't participate on the electronic bands, like very much. Like it's there, it changes a little bit your band gap, but not really. Like if you were to remove it and just compute the band structure itself, like how your energy levels are aligned, you will get basically the same thing. It's just a small shift in energy. Mm-hmm. Yeah. So like it depends. It depends on the material. Sometimes all atoms contribute. Sometimes no.
Yeah. I'm really getting a sense for how many different perovskites there are and how differently each one behaves. Yeah, like I know you said it before, but I can't imagine going to a conference and just seeing like all these different materials that are all technically like the same thing, but just are like under the same umbrella term, but they're very different in the way that they behave.
Yeah, usually like in conferences, the symposium, let's say they're broad, like it's like perovskites. So you can pretty much show any perovskite that you want, as long as it's a perovskite, you know. So it's I guess it's okay. Sometimes it's a little bit hard to convince people that something is a perovskite when it doesn't look like it. But as I said, like nowadays the perovskite term is kind of almost lost. There are so many of them.
And so when I'm designing a perovskite for applicational use, let's focus on solar. Why does that density of states matter?
So it depends. It depends a lot because, for example, very recently we did this work where you were studying transport in 2D materials, like 2D layered perovskites and 3D layered perovskites, because there's this thing that we didn't understand, like as a community, because like your perovskite plane in a layered perovskite is exactly the same as you have like in a 3D perovskite. It's just like something that you stack a lot of layers of the same thing and you get like a 3D material. But if you look at the transport of the charges in plane, they are different for layered materials than on 3D materials. Even though like the perovskite plane is pretty much the same, but the transport is much smaller. So yeah, so like this is one of the things that we wanted to figure out why, and eventually we did track down as being like something that's coming from density of states, because like you just like have so many carriers concentrated like in a 2D region, because before you have 3D, so like they're much more diluted, and when we reduce the dimensionality, they all like get very densely packed in the 2D plane. So like since you have a lot of carriers, like all these electrons, they are like scattering each other, you know. So when you have too many balls in a room, they start kicking into each other. So like this reduces the mobility of the materials. Yes. So like this is one example, let's say, of where density of states can impact a lot.
Okay, yeah, that gives me some clarity. I was reading that paper last night actually, and I was having a little bit of trouble understanding that aspect of your results, so that helps a lot. It seems like almost a little non-astonishing that like in your n equals 1 you would have a different density of states than your n equals 2, and comparing that to your 3D, because you just have like in your 3D so much more stuff going on. Like there's so many more free variables and how things can move and things like that. At least like maybe I'm thinking too much in like a phonon sense of like things moving around and stuff, but is that like an accurate kind of way to think about it?
Yeah, I think so. Like, if you look at the density of states plot, like usually you have like some sort of curve. Let's say something like this, almost like not a parabola, but something like this. So like a yeah. So like when your density of states goes to zero, like this, usually like this part is the top of your valence band. So like this for the 3D material. So like what happens, for example, for n equals 1 is that you have like this very big step function. So like since you have a lot of carriers in your material, like close to the band edges, close to this part where it goes to zero, you have a lot of carriers. So like your density of states here, let's say, it's like a step function. Then when you go to n equals 2, the step function goes a little bit down because now we have a little bit more degree of freedom for the electrons to move. So like the density of states is reduced a little bit. And if you keep like adding layers, eventually you're going to reach the 3D limit and you're going to get sort of like a square root of energy, which is a very characteristic of 3D materials. Just because you have like a bunch of space so the electrons can go away from the band edge, you know, which they cannot on the layered case.
Is the relationship between these different like molecular geometries and then the density of states? I mean, you're saying that like the more complicated it gets, and then eventually when you reach like a 3D structure, then it's square root of your energy, roughly. Roughly. Is that relationship pretty linear, or?
For modules, like where people observe that is usually like tight binding modules. I don't know if you're familiar with, but
What type of models?
tight binding models.
Okay, no idea.
Yeah, it's just like a let's say a simplistic Hamiltonian where you just perform like you write your Hamiltonian as a combination of like molecular orbitals basically. So you calculate these hopping terms between like the different sites in your material, like let's say from this site to this site, and then you calculate all these energies like to blah, blah, and you can construct a Hamiltonian for this like a model. It's not like first principles, you know. So you have like a tunable parameters. But you can use that to show like this relation. So like you can construct this tightly binding model for very simple layered systems, and you just start like putting more layers, and you clearly see like this going from a square root to like a
Okay, cool. Yeah, I guess I'm thinking about it because all the modeling that I've ever done is, or like I've ever participated in, is been ice modeling, and so more specifically like thermal and kinematic models of ice. And the way in which it behaves is pretty nonlinear. So if like, I was actually explaining this in another episode that by the time this episode is released, it will be out. It's with Dr. Ben Kiesling, so go check that out. But basically, like, let's say heat conduction in ice, right? Totally ignoring the way that ice flows and like its viscous behavior. Just like pure conductivity of ice is a function of heat capacitance, which changes according to temperature. So as you're warming up ice, you're actively changing the way in which heat flows through ice. And same with cold. So if you're cooling ice down, you're like, your output becomes an input. And so you get this really weird relationship where you can have like the same circumstances, or like really, maybe not the same, but like really similar, like a similar starting point, or like really similar environmental factors in a different model run, but you'll get like completely different answers on each run just because of this like nonlinearity and the way that it the way that it's difficult to kind of model. So I'm curious if there's any relationships like that in the modeling that you've done.
No, not really. Like at least like usually within let's say ab initio approaches, things are like they're very deterministic. Let's say because this is all based on like very fundamental principles of quantum mechanics.
Yeah, so ab initio meaning you're not using any like experimental or observations.
Yeah, anything like related to a parameter that you can tune. If you like you have a parameter that you can tune and changes your result, this is not ab initio. So it's also called first principles, I guess. Yeah, so like usually in first principles, these things are more, let's say, deterministic. So like if you were to compute like the band structure for of a material, it's always going to be the same band structure if you use the exact same calculation, let's say, for the same material. Yeah. So usually I don't think these things can happen. Maybe, I'm not sure, for like a heat conductance, like in solid materials, like crystalline materials. But this is like already not my field.
Yeah.
Yeah.
What's the benefit of ab initio as opposed to, stating some boundary conditions or having some like parameter that you can kind of tune? Why conduct things from first principles?
Yeah, because I think it's a bit hard for you to tell. For example, if you want to calculate a property of a material, let's say transport, and your theory has a parameter that you can tune and can change your property, you can like give whatever value you want to match experiment. So that can be helpful to understand some things, but it's not predictive, right? So like what we want to be able to do with first principles is to be able to predict things, like so we can not only like study materials that already exist, but also materials that don't exist yet. So we have to be able to predict things, otherwise this doesn't work.
Yeah, like you don't even have observations or like material constants for some of the stuff that you're trying to create because the material either hasn't been created yet or just hasn't been researched in the type of way that you want. And so you have to like basically grassroots, just like build it from the ground up.
Usually we start from like a experimental basis, at least for the crystal structure, like because you have to input, like as I said, you have to input, let's say, your material for your calculation, right? So you can invent a structure that doesn't exist. That's totally fine. Then you can run the calculations and see what you get. But you can also, usually what we do is like based on something that already exists. So people refine the crystal structure via XRT or whatever. So we know how the atoms looks like, and we just like use that to do our calculations. Then besides that, there are no really like free parameters.
What is a vacancy ordered perovskite?
Yeah, so this is the LED case that I was discussing before. It's these
Okay.
octahedrons that are kind of like isolated by,
Okay.
from each other. Like you have octahedral, vacancy, octahedral, vacancy, octahedral. So it's like a double perovskite where one of the sites is empty. Yeah.
And I guess while we're kind of focusing on the modeling, does modeling differ a lot whenever you're modeling perovskites in regard to absorption for solar panels and things like that, as opposed to emission for LEDs?
Let's say the procedure, like the modeling, like how we study these materials, it can change quite a lot. Yeah. Usually, for example, if you're for solar cells, you are interested in band structure, so you can know the band gap. You might be interested in transport, which what we were doing on the previous paper that we were discussing. Absorption coefficient is something super useful to calculate. Like for LEDs, you might want to be able to like also include like higher levels of theory, because usually like the standard, like let's say base level density functional theory that you use as a tool to study these materials is not like applicable for extonic cases. So you have to extend the methodology, and like things get much more complicated and much more computationally expensive as well.
Yeah. That I would imagine that's a big challenge in
For
these
sure.
models, because it seems like these systems can really run away from you computationally, like in their difficulty to model and their computational cost really, really quickly.
Yeah, for sure. I mean, we don't really like run calculations on our computers, right? We
Oh, of
usually
course,
run the
yeah.
supercomputers like Frontera, TACC here at UT Austin, and some others as well. Yeah.
Actually gonna have the director of TSAC on here in a couple weeks, so that'll be cool. They're doing some big news, or he's got some big news to share when he comes on, so I think they're having I haven't done too much research on him yet, but they have like I guess like a new computer that they're coming out with or something pretty new.
Yeah, I heard about it. Yes,
Oh,
maybe
okay.
I don't know if it's the Frontier one, but they have some new things coming up.
Huh. Okay, cool. So when you're modeling these perovskites, when you have like n equals 1, n equals 2, it's a very like small nano-sized system. I mean, it's like a couple, not a couple atoms, but like a couple different crystal structures. Um, so how can you model something that small and then have it be representative of like a more macro scale, like
Yeah,
solar cell?
I mean, basically, any crystalline structure has a small repeating building block. You know, we call it like a unit cell. And like as long as you can impose boundary conditions for this thing, you can represent your system with the unit cell, because then this thing will just replicate and like create something that's infinite in reality, right? So we always try to look for this building block piece, like the unit cell. And usually it has, of course, much less atoms, because we are not talking about like a structure that's like, angstroms or nanometers of like size. It's just like a couple atoms apart, just
Okay.
like 5, 6.
How do you constrain, like, or I guess what tells you this is the size of my unit cell? Are there different parameters that like would behave or like that would predict behavior of the entire crystal lattice?
Yeah, sort of. I mean, it can be quite a pain to figure out like what's the best, let's say, unit cell to represent a system. Perovskites is one case that I can give an example, because it's something that I worked with. Like if you look at the perovskites, it's these octahedrons that are corner sharing, right? Like they are just repeating in 3 dimensions. So if you were to have like a perfect octahedrons where they are like all connected nicely, like no distortions, no rotations, nothing, you can describe your system just with one octahedron, because that's the only thing that you have, and everything is just a repetition of that. But like in reality, octahedrons, like in perovskites, they can rotate. So like they are not like connected in a straight line; they are just a little bit rotated in relation to each other. So in order to describe this type of rotations, you would have to have 2 octahedrons in your unit cell instead of 1. And it can get more complicated where you can have 4. So it depends on it usually depends on the phase that you're looking. So this is like the phase that we call like orthohombic phase, cubic phase, in perovskites, and so on. So it's material dependent. But, it depends on the phase that you're looking, what you're trying to study, but you try to go down and find this building block piece. Yes. Usually this is something that people can measure, by the way, so we don't have to like construct it by hand.
How do people measure that?
Yeah, that's a good question. Usually XRD, most of the times I think you can get, because as long as you know the Bragg reflections, you can reconstruct your crystal.
Oh,
Yes, like the XRD combs, it refracts around inside your material. You can use that to reconstruct your unit cell.
when you talk about the rotation of the different compounds, is
Yeah, the
compound the right word?
octahedrons, yeah.
Yeah. Do you have rotation not only in like this kind of XY plane, but like in the
Yeah, in
Z
general, you
and
would have like in 3 directions.
yeah.
Usually in layered perovskite is more like an in-plane thing.
Mm.
Depends on how close the layers are, but in general it's 3 dimensions. Yes.
Okay. And does that orientation of crystals change at all due to any kind of environmental factors?
Oh yeah, for sure. I mean, like when we say that like it's a bit rotated or something, this is just like a static picture, right? Because like in reality, this thing is like moving around. Yeah. So that's what people do, for example, in molecular dynamic simulation, which is not what I do, but they kind of do this evolution in time, so they can see the atoms vibrating. Like we see the vibration of atoms as well, but from a different point of view. We use like phonons. Like we use the phonons dispersion to figure out like how your system is vibrating. It's like a static picture. Yeah.
Yeah, I know that ice has these crystal fabrics in it that orient themselves perpendicular to the maximum stress vector. So if I have ice that's sliding down a hill, then that like vector of maximum stress will be this way. So those crystals will like orient themselves like that, just like over time. And that changes like even its conductance, so like its dielectric properties, so the ability to send an electromagnetic wave through it. When you like orient the crystals in such a way, then you would have like less attenuation, so that wave is losing more energy as it travels down. does something like that happen? Maybe not because of like stress or something, but like if I'm putting a perovskite cell outside, is there environmental factors that are kind of changing the orientation of those crystals and making it maybe less efficient?
Yeah, for sure. Like heat and light do that. Like light can contract the octahedra. Like if you shine light inside the perovskite, you're gonna see like a small contraction of your system. So this is also something very new. Let's say people found out like 2 years ago or
That's
something.
really cool.
Yeah, it's pretty cool. So the same thing, I guess. Let's say. Yeah, I think that's the only example that comes to my mind right now. Yeah.
You mentioned heat?
Heat. Yeah, I guess this could happen to heat as well, but I'm not sure.
Okay. Yeah, yeah. Like,
Transport, for example, for sure as well.
Yeah.
Like depending on how you orient your crystal. Like if it's a layered material and the layers are like in the XY plane and you try to conduct like something in the perpendicular direction, you're gonna get almost no current. So I guess this could be like direction dependent as well.
Gotcha. Yeah, because, I mean, when you put solar panels on a roof and you point them at the sun all day, they're going to heat up, right? So how do you protect the material that you have and protect its efficiency to conduct electricity when it's kind of being heated the whole day?
Yeah, that's a good question. Some people try to put these like protective glasses on top, but this is like very like an engineering problem, I would say. Like it is something that people are actively working on. I don't think there's like a straight answer. There's also this problem that, for example, you put a solar panel on this table and you try to collect light, but like the sun is like moving around during the day. So like sometimes it's gonna be heating like this, sometimes it's gonna be heating like this, and this changes like the way that your material absorbs the light. So unfortunately, we cannot make a solar cell that can change shape over time, but it would be very interesting.
That would be really cool. I saw in a YouTube comment somewhere that the perovskite, it was either the tandem cell or perovskite, it absorbs so like that spectrum window of light that it absorbs isn't affected by like seasonal changes. So like there's different wavelengths of light that hit the earth when it's in winter versus when it's in summer. And I think you have like infrared losses in winter versus summer. And a lot of solar panels capture some of that infrared light. And so in winter, there'll be less output than in summer. But with perovskite, that doesn't affect it. Is that?
I guess it's just affected maybe less.
Okay.
Just because they absorb light very well.
Yeah.
I would say they have like a large absorption coefficients as well.
How much of an impact does it actually make on the technology, though?
That's a good question. I mean, based on what we know, I don't think it's too much because like usually people take these things into account when they like are trying to probe like the stability of the perovskite and the efficiency of the perovskite.
Yeah.
Right. If you're trying to measure the stability, you have to shine light. So you heat up your material and the efficiency that you see is like already taking into that into account. You see what I mean?
Yeah, I see what you mean. And then with these tandem cells, so when I layer my silica on top of my perovskite, is it silica on top? So silica would be closer to the sun, and perovskite would be below.
Yeah, I believe so. Yes.
Okay. Definitely have a couple questions. First of all, why put your silica on top and your perovskite below?
I guess it's just because you want to be able to because the spectrum goes like this. So first you want to be able to have the material that absorbs, let's say, the first part of your spectrum, then the second part of your spectrum. If you start mixing, like you put one before and the other one after, you start having this hot carriers problem. So you start losing like carriers to heat, and you don't want to do that. So you want to extract like the photons that you can, like the best way that you can, and then you proceed to the next layer.
That's what this building is doing right now. It's like, well, I think it's cooling down right now, actually, and then contracting back. But, yeah, when I come here in the morning, it's a little off topic. I'm sorry, but I think it's a cool thing to say. When I come here in the morning, the sun is shining like right on it, so the building will like creak and creak and
Oh, yeah.
creak, and I'm pretty sure that's because it's expanding a little bit due to the heat.
Yeah, for sure.
And then as the sun sets, it kind of contracts back. Yeah, so silica's on top because you don't want like differential layering of that perovskite and that silica so that your energy efficiency is less and then you're losing more stuff to heat. At that perovskite silica interface, which may be a bit of a far out question because I don't know how much of this is actually in your realm of expertise. But at that interface itself, how are those two kind of crystals behaving? Because perovskite is going to be, perovskite's octahedral. I don't know about the silica, if it's the same. And they're not bonded together. And so I would imagine that there's like more atomic space between them. And so I guess thinking on a macro scale, there's not going to be a huge difference because they're touching each other. But on a nano scale, I wonder what kind of physics you would get at that interface.
Yeah, we wonder that too. Yeah, like this is something like people are doing right now as well. Like mixing silicon and perovskite is fairly new technology.
Yeah.
But like a heterostructure, let's say, where people trying to sandwich two different materials is something very old. So I don't know. It's kind of like a material dependent what happens in the interface, but you can have like a phonon modes like that are arising, let's say, just because of this contact of the interfaces. Like these modes can lead your material to be unstable if your materials are too different from each other.
Mm-hmm.
Sometimes it can help a little bit, like the stability.
Yeah.
You can form dipoles, which can like change a lot, like the way that your material absorbs light as well. So like there's people that work a lot on this, like let's say interface physics.
Mm.
Yeah, some people in my old group in PhD were doing that a lot.
Okay. Yeah, that's really cool stuff. Yeah, I'd imagine interface stuff can get pretty weird because, like, if you have like a relatively homogeneous material and like you're able to constrain small heterogeneities, so like, you know, the different rotation of your crystals and things like that, I'd imagine it's not. It's possible to model it, which like your research is pretty much living proof of that. But I wouldn't know how that would actually like behave at that interface, but it seems really cool.
Yeah, I think that's the whole like beauty of the field is because we don't know how to do that either. You know,
Yeah.
like our job is to try to come with some ways to model these things.
Yeah.
It's the same thing with like the layered perovskites because like you have the perovskite network, but then you have like this huge organic cation in the middle.
Mm-hmm.
We cannot really like simulate very complex things if we include like everything in your calculation. Let's say the organic layer and the inorganic layer. So it's just too many atoms. So like what we usually do is that we strip the organic cations out and we just are left with like an inorganic network. And what we can show is that this network actually behaves very similar to the full material to motivate a little bit. So like sometimes you have to find these tricks, you know.
Yeah.
Yeah.
Yeah. I think I understand that pretty well. With ice, I'm thinking of like, so a big interface in ice physics and modeling ice is that like bedrock ice interface. And a lot of the times there'll be like sediment there, and if that sediment has a lot of porosity, so like, or like depending on the porosity of that sediment, so the sediment has a lot of water within it and a lot of little pores in it that can hold a lot of water, then the actual like thermodynamic components and then like scattering of like, so if you bounce an electromagnetic wave down there, the scattering of the wave will act completely different. And the same thing with acoustics too. So if I have a kinematic seismic wave traveling through the ice, and then as you reach like a impedance contrast. So I can't think of a good way to connect it to your stuff, but basically like impedance contrast, meaning like this top layer can allow sound to travel through it differently than the bottom layer. So this would be like you have an interface between, I mean, I'm sure you might deal with this problem with like carrier charge mobility through silica and then the perovskite underneath. So you might have like an interface there, and I'm not exactly sure. I guess if you think about it kind of like a wave, then you would have like refraction and reflection at that point. But anyways, so depending on how much water is in that sediment, it'll like completely change the polarity of that wave as it, reaches that interface. So usually what will happen is like if I go from, oh my God, I hope every geophysics professor that I have isn't watching because I just forgot something very important. But I think when you go from, if you're like delta impedance, so basically like if it's easier to carry sound through this medium and then harder through the other, then I'm going to have like a positive to negative polarity and then back to positive. So that sound wave is going to go like positive, negative, positive. And then if I have the opposite, then I'll go like negative, positive, negative. And just at the interface, if you have like this really small difference in porosity, it's like a couple percent, it'll completely change the behavior of that wave there. And the universe imitates itself, right? Yeah. So I would wonder at the nanoscale, at that interface, if you would have similar things going on where just tiny little changes in something create like actually like pretty big observable effects.
Yeah, so for example, from the phonon point of view, which is like what we do here, there's someone in my group that's working with like how, let's say lattice vibrations of one layer would affect like the lattice vibrations of the other layer, or like the carriers of the other layer. Because even if like they are not connected or just are very close, these two things, they are oscillating. And turns out like the oscillation of this guy actually affects the other one, even if they are not like very close to each other. Yeah. So these things can definitely change like your properties. So like this is something that we would like to definitely to understand more.
Yeah, I wonder if like, because I remember you talking about like, excitons, and how basically if you move an electron through space and you move it from one location to another, then around that space you're going to create a vacancy, or you're going to create like polarized space around it. And when you're vibrating an atom through space at like an interface like that, even if you vibrate this way, maybe there's not like a really strong, what is it, like Coulomb forces that are between those? Okay, really strong coupling. But that polarized space that you have, maybe that is able to interact with it.
Oh yeah, 100%. Like that's exactly what you want to know, because you can like have changes in one layer that can, I don't know, generate dipoles that can like scatter your charge carriers via an electric field or something. It might be just really like a mechanical wave thing, and usually it's like not every phonon mode that would like interfere between the two layers. It's like some specific modes of vibration that interacts more. The same thing goes for transporting pretty much anything like electron phonon. It's never all of them. It's usually like some specific ones.
Yeah, that answers that earlier question I had about like different modes of vibration being at resonance, or like mimicking resonance. That answers that perfectly. That's really cool. Yeah. Is it like, so like this phono mode is vibrating another phono mode and then they're going to amplify each other, or like, is it even right to think about like amplifying each other in this
like
weird
a
quantum
different phono
space?
mode? That's a good question. I'm not sure. I'm not sure if people know that. I can tell you that, like, for example, phono modes, they can couple differently with like a charge carriers. Yeah. Like phonons, coupling with phonons is a little bit more complicated already. Yeah, you see.
Yeah, that's. I mean, you can really get into the weeds on like that.
Yeah, because
Quasi-particle
in
stuff.
the end, like our field is like always divided in these different types of couplings. You have like electron phonon coupling, you have electron photon coupling, and so on. Like all of these things give rise to different effects. You know.
When you talk about like going back to that analogy of like putting an electron into a space and then you polarize that space because of the charge of the electron. I know phonons don't have charge, but maybe with like vibrational energy or something else, are you like, if you have a strong phonon vibration in one area, is that creating a vacancy elsewhere that is like kind of like a particle?
Not necessarily. Like the way that the phonons couple with electrons, it can be like many ways. For example, you can have a phonon moles that are like polar, that we call. Like they are polar because like when, for example, you can imagine that you have a positive charge and a negative charge. So you pull them apart, you generate like an electric field. Like if you have like a concentration of a negative charge and you pull them apart, there's an electric field being generated. Right, so like some phonons, they vibrate like that. So like when they are vibrating, they keep forming these electric fields. Like they go and go away, they come and go away. So like there's this type of coupling that we call Frolic coupling, which is like when the charge carriers, the electrons, they couple with this electric field, which is being generated by the vibration of your crystal. But you can also have other types of coupling, like a deformation potential, which comes from like these acoustic waves. It's a different thing. It's not like coming from electric field. Is more like a vibration, like a wave. Yeah. So it depends. You can have many types of electron phonon coupling.
Yeah, and then there's thermally generated ones too, right?
Yeah, for sure. Electron phonon is actually behind like thermoelectrics and stuff. It's not my field, but there's people in our group also investigating thermoelectrics.
Yeah, I was about to say, I would imagine that like sound phonons, I mean, I guess if you're outside and it's like a loud environment or there's like wind hitting your solar panel, you might generate something, maybe.
Like a microscopic, you mean?
Yeah.
Yeah, definitely. Like, I guess I mean you can have like a piece of electricity, right? When you like press a material and it generates like electricity. Yeah. So like you just apply stress and it generate electricity. You can make this stress of like a oscillating time, and you're gonna have like an oscillating piezoelectric if you want. So yeah, for sure. Like there's a bunch of these things that like a macroscopic effects that can affect like microscopically as well.
Yeah, and yeah, you could really get into the weeds in this because there's like, okay, you have the sun hitting it at different angles during the day, so maybe like there's going to be variability in how that solar cell is heated spatially. And so if you think about it like a 2D plane, like maybe the top is more heated than the bottom, and then you have like this like thermal effect on your phonons or like your phonomodes at the top that you maybe don't have at the bottom, or maybe vice versa. And
yeah, it could be definitely.
Yeah,
I mean, a bunch of things can happen if you start playing around with it.
Yeah,
yeah,
it's really cool stuff. I mean, how far out do you think we are from being able to like kind of, because it seems like the questions that I've been throwing at you are like very theoretical, not super easy to model, are almost a little vague and like unconstrained. How far out do you think we are from like being able to model these systems pretty well and then like really get into the weeds of like different?
I think right now we are already in a very good stage for like the methodology that we have, right? Like there's things that we cannot do yet, but like for what we already have, they're working quite well. Like you can simulate, I don't know, transport, electric transport in a material, and like usually we get amazing agreement of experiments, you know. Same thing for optics, optical absorption. So like theory-wise, I think we are pretty good. Like So of course there's still like some developments to make, which is always like this very big loop, because we need a lot of computational power in order to do better calculations, but we also need better calculations to understand how we can make better materials to have better computers. You see, so you kind of enter in these circles, and sometimes things kind of go slow.
Yeah.
On the experimental side, let's say practical side, as I said, I think at least for the perovskite point of view, things are going very good. Yeah. So if is it the future, we are not sure. Right? Maybe there's another material that's going to be better in the future, but it's for sure a step.
It's hard to say. Do you have any specific things in mind in the literature that seem really promising?
Oh, seeming very promising. Let's say, I think the most promising thing right now for me, my concept, is this 3D, 2D heterostructures. It's like you mix 2D and 3D perovskites. Yeah, because you can try to harvest the very good efficiency of the 3D materials, because we know they are very good, but they're not very stable. But you can get this stability from the 2D materials that you are mixing with the 3D when you make these sandwiches. So people found out that when you do that, you can retain a very good PCs, but they are stable for much longer. So this could be a very promising path for solar cells in the future. We don't really know yet, but
So 2D sheet, 3D, I guess meat of your sandwich. 2D sheet, 3D
Yeah.
meat.
yeah.
Okay. How thick are those usually?
Oh, that's a good question. I'm not sure. Probably a couple nanometers.
Well, what about the whole cell itself, or the?
Oh
all
yeah,
of the perovskite?
I think it strongly depends, because if you start going in the photovoltaic field, everybody has its own favorite sandwich, because you have the absorber, then you have, I don't know, transport layers, you have this layer, and then you get a very big sandwich thing. So it depends which materials you put there, which what you're choosing to be your contacts. This can vary a lot.
And where do you think perovskites rank in reducing the cost of solar? I know that's probably the biggest thing that people like to talk about when it comes to solar power.
Yeah, I can say that I think they are as cheap to produce as silicon. So money-wise, it's not a problem. I think the biggest problem is, as I mentioned before, is more the market being flooded with silicon, which is not a bad thing. It's just what you have right now, so it's a bit hard for you to make this jump over silicon. And yeah, stability-wise is something that we also have to fix, right? So that's what we are working right now, because even if we can put them into the market, if they are gonna break down in 1 year, it's not very good, not very profitable. Yeah.
Okay, well, I think that's all the questions that I could throw at you.
Yeah.
Yeah. Thank you so much for coming on.
Yeah, thank you.
This has been a really fun conversation.
Yeah, thank you. I had a lot of fun too.
Yeah. I've been researching this stuff a little bit, and it was pretty difficult to wrap my mind around the quantum physics, and I tried to write down some of the equations and tried to understand it, and I think it really helps me to try to connect it to spring systems and things that you can observe in the macro, and then also you definitely notice I'm trying to connect it to ice physics and things that I can
Yeah, and that's very good,
understand.
I think, because you can get a lot of interesting ideas from other fields.
Exactly.
Yeah, that's super nice.
I had oh man, I forgot his name. Nope, can't remember. There was a researcher. I went to it was a little grad school introductory, what to expect from grad school. Should you go or should you not? And there was a guest speaker, as a researcher there, and he said this really cool thing that stuck with me. He was the best research comes at the intersection of multiple fields, because that's where you really get creative ideas. Because I think you do start to get, just you can get into the weeds of all of this, solar cell stuff and all of that, you can really get into the weeds of like the philosophy of science and how to approach scientific problems. But I think that a lot of different fields think of problems differently than others, just because like a lot of ideas in fields or like researchers come from like a handful of advisors that think of it in their way of thinking about it, and then they kind of all have all their grad student grandkids that then turn into researchers and postdocs, and then eventually they become faculty and they have their own students and they teach their students what they were taught. So you can get some like bias in how the problem is approached. And so it is really refreshing to like take concepts from a branch of science that it's untouched by the other and then try to merge the two together.
Yeah. I think this is very nice on our field, for example, because it's very mixed, like we have like chemists, we have like, I don't know, engineer people, physicists, as myself. So like when you put together a bunch of people that work in different things, like everybody kind of contributes with their own way of thinking, Yeah. That's very, very helpful. Yeah.
Yeah. I mean, there's definitely this idea of like, from what I saw, your group seems pretty international. Like it seems like you guys are pulling people from all across the world. Yes. And so not only is your approach to science going to be different from just like how you were taught to understand the world, because your culture is different and your education was different, and the country you grew up in was different, but like your actual advisors are different. And so like you are bringing this like scientific perspective that you developed in Brazil and then Florianopolis and then France and Belgium, and then you're taking it to the US in this research group in Austin. And then it seems like you have some Chinese colleagues and
Chinese, like, Korean people,
yeah.
Vietnamese people.
Yeah, and that would be really cool to see that interplay. How does that, like, do you find that your colleagues from other countries approach the problems a bit differently than you?
I think so, but it's also hard to say because everybody has kind of its own expertise. I don't know, there's some people in our group that are physicists, some of them are engineers as well. So I guess everybody kind of contributes in a different way. So that's why we like to do these group meetings. Like we do it like every week just to chat a little bit about what we've been doing, And this is very helpful because, I don't know, like sometimes someone that knows a little bit more about chemistry can give you like some very nice insights in something that you're doing and you didn't realize because you're like a physicist. Yeah.
It almost seems like, granted, I don't have very much experience with private industry, but from what I've heard from people's anecdotes, it's like a lot of research done in industry is done by like a select handful of like, they'll call you like a area of study expert or something. It depends on the company, but basically like if there's a company won't want to hire like 10 guys all to do statistics. Like they'll hire 1 or 2 guys that are really good at statistics, and then those guys will meet up with the 1 or 2 guys that I guess in geology are very good at like seismic interpretation, and then those guys will meet up with the 2 guys that are like really good drill engineers, and they're all like PhDs, experts in their subjects, but they're super different fields. They're all kind of like interplay with each other, and it seems like your research group is, or it sounds relatively similar to that.
Yeah, I think so. Both of them, both like the actual one, like postdoc one and the PhD were like that. I don't know. I think it was when I first started my PhD, I was a little bit, I don't know, unsure because I was going for a PhD in a chemistry institute and I'm a physicist, which was never a problem. I was just like, I didn't know how it was going to be. And in the end, it was like super nice. Like it was so nice. I had like one supervisor that was like physicist, the other one was a chemist. And like, I don't know, I learned so much because of that, If you have like this opportunity to go to and talk to people from different fields that are working in things that are similar to yours, it's super good, super fruitful.
Yeah. And your research itself is a really nice marriage of chemistry and physics.
Yeah.
It makes a lot of sense that you had a chemistry and a physics advisor.
Yeah, and technically my PhD is written material science.
Yeah.
Just because I didn't want to put like one or the other. So it put like the middle ground.
Nice. Yeah, I was hesitating on what. I mean, I know science is becoming increasingly interdisciplinary, so like, especially in the next couple decades, like it might be kind of outdated to call someone like a material physicist or a civil engineer or something, because you're just using so many different things. And semantics change with time. But in your words, what do you think would be a good title for you as a scientist?
Oh, I think like probably either a computational material scientist or a material scientist, because it's a very complicated say. I see myself as a physicist, but I work in a field that's very like mixed. So you can find people doing things similar to what I do, but they're just from different fields, and I never like touched physics. They're, for example, just like pure chemists, you know. So am I a chemist? Am I a physicist? I consider myself a physicist with like strong background in material science. Yeah.
Yeah, I run into a similar problem with, so polar geophysics is like basically glaciology. There's like so much glaciology that like I couldn't call myself a glaciologist. I'm just an undergrad, but like a postdoc or a faculty member, they could probably get away with calling themselves a glaciologist, but it's just so like a glaciologist at one institution is going to be doing something completely different than a glaciologist at another. And it's like it is weird how like as more and more people get involved with science too, because I feel like more people are getting their PhDs in general. I actually don't know if that's
I don't know.
if
I
that's
hope it's
accurate.
true, but
I think, okay, if I'm wrong, I'm gonna put like a little disclaimer that I was wrong, but I'm pretty sure that at least in like first world countries, the level of education is rising, and I think there's more people getting PhDs. And so there's more people entering science, and so there's more of a blend of perspectives and like your kind of linear terms for what a certain scientist is just kind of,
yeah.
it's kind of thrown out the window. And I feel like we're struggling to find the right semantics because we've been using the same words for so long. So like glaciologist, I study glaciers, but like, or like material scientist, I study materials, but like computational material science.
Yeah.
Like how do you now you have to tack on another term,
Yeah.
and then how many terms are you going to tack on? Yeah.
There's no answer,
Yeah.
right? Like
Theoretical, computational, material,
yeah. I mean, I
physiochemist.
think in the end it all depends like where you get your permanent position. Let's say if you're like become a professor like in a physics institute, you're probably gonna be known as a physicist. But it's like a bit of for yourself as well.
Yeah, it's like, what do you want to be called?
Yeah, because like as I said, like, for example, if you look at my undergrad, it's like physics, like the title is physics. Then like it goes to PhD is material science. Like which one is it? I don't know.
Yeah. Yeah, it definitely gets tricky because your personal title definitely matters. It definitely matters. But I feel like your dissertation title matters a lot too, like what exact field that you're going to go into, because that kind of defines like your expertise.
Yeah, it's like at the moment that you started like working actively in one field, people will know you by your name and your work, you know, not like by your title. So I guess like at the long term it doesn't matter too much, but might be interesting for some things like websites, curriculum.
Yeah.
Yeah.
What about like, so when you're picking like a topic for your dissertation or a certain title or what field to put it under, do you think about like how the title of that, even just like the short worded title, is going to affect like the research that you're going to do in the future? Because if you're going to get a postdoc job somewhere, the first thing they're going to read is the title of your dissertation, right? And they're going to be like, okay, this guy does this. Yeah, how careful is that titling?
I mean, for the title of your dissertation, I guess it just depends on what you end up working with. Like, I don't know, like when I started my PhD, I had like a project that I was supposed to do. But in the end, like what we did was completely different. Just because like things were coming to us, like projects, and we were just like going through them. And then like my PhD was something totally different. So we just like I gave a title to my thesis that kind of like incorporates a bit of everything that I did. Let's say perovskites, ab initio, methodologies, and stuff like that. So like I think we at least we try to like just comprise all these different key terms in the title. In the title of the dissertation. People will also work at your publications as well. So I guess you can also think that the title of your publications also matters. So.
And there's like, when you're talking about semantics, there's always like language barriers and difference between like, I don't know. Here's a good. So I took Japanese last semester, and the way you say geophysics in Japanese is, or my Japanese teacher told me that it was chiri butsuri gaku. So, oh man, I think chiri is geo, like geology, and butsu is like physics, or butsuri is like physics, and gaku is like study. And but I think if you said that in Japan, or like to a Japanese researcher, they would be kind of confused on what you mean, because there's like this like semantic difference, and especially with like Japanese or any like Chinese lettering, it's pictographic. So like in a good example is like in Mandarin, the word or like the letter for self is the same as the letter for self in Japanese. It's like a character. But if you were to say the word for self in Chinese, it would be completely different from the word for self in Japanese. So yeah, if you were Japanese and you like read a newspaper in Mandarin or like Cantonese, you'd be able to kind of get the gist. But if you read it out loud to like someone who spoke Cantonese, they'd be like, "What are you saying?" So there's like this. Yeah, there's like little nuances in semantics when it comes to defining things in research and science. Oh, I think my phone has limited storage.
It's okay.
Yeah, so the audio or the video cut out, but I have so much audio space. So I'll probably just, I mean, if you're listening this far in, you probably aren't watching it. You're probably doing some kind of chore or something in the background. That's what I would be doing. Yeah. Yeah, I think that's about it. That's all the questions I could throw at you. And yeah, I don't want to take up too much of your time too. I know we said we stopped at 5.
Yeah. Thank you. I hope like I was able to help you with something like to understand a little bit better.
Oh,
people
yeah.
to understand a little better too, because I mean, I guess it's part of like our job to share science.
I think if I run with any idea that I gain from this conversation, I'm gonna listen back to it. So there's like more stuff that I'll glean on a second and like third listen, especially this conversation, because a lot of the stuff, like to be completely honest, went a little bit over my head. But like I have a decent physics background, so I could understand a lot of it. And I think on like a second or third listen, I'd be able to understand it a bit better. But if there's an idea that I would glean, it was thinking about those hydrates and if they're similar to perovskites in any way.
Yeah, I'll take a look, definitely. I'm curious now. Hydrates.
Yeah, so clathrates, it's like water molecules freezing in a crystalline cage structure around some kind of gas. The most common is like methane. They're all over the bottom of the Gulf of Mexico. And
okay, well, it's like is it like actual ice?
yeah, but it's not ice per se. Like the crystal structure is different than ice. I know that radar attenuation barely changes, if it changes at all. But and acoustic impedance doesn't change much, because like I think that gas molecule, like the acoustic waves just travels through the frozen water molecules and not really the gas. I actually
Yeah,
don't.
I see.
Yeah. But like, it's like it traveling through a honeycomb, but then you negate that air. So it like, for some reason, like there's not like a bunch of free space between it, since you have a molecule there, but I don't know. Yeah,
Interesting.
I'd have to look
Yeah,
more into
I'll
it.
definitely look into it.
Yeah, I don't want to say too much stuff that I don't know what I'm talking about. But I wonder if you could like look at some kind of difference in conductivity in some way, as like a geophysical means of saying where hydrates are. Because a lot of geophysics is like using a physical observation. So like, how do sound waves bounce off this thing? How does a electromagnetic wave bounce off this thing? What kind of light is this reflecting? What's the speed of sound in this?
Yeah, I guess the
medium.
medium matters a lot. Yeah.
Yeah, so it's like basically when I throw different physical phenomena at this thing, how does it react to that and how does it behave? And then what can that tell me about what that thing is? That's like the observational geophysics. And I wonder if you could do something with conductivity and like different crystal structure. That'd be pretty cool.
I mean, yeah, definitely. If you can like refine a actual crystal structure of that, you can definitely run calculations on it.
Yeah, that'd be cool.
Yeah, for sure.
Yeah. Well, yeah, thank you so much.
Yeah, thank you.
I know I've said thank you like 5 times already, but I really am very appreciative. I think I told you this in the email, but if there's anything you want to promote at the end, and if anyone wants to contact you, ask you questions or anything, where can people find you?
Yeah, I mean, I work at UT Austin, so like you can easily find my email anywhere. You can definitely like send me a message anytime if you want to chat or ask something about the talk, like at the podcast. I mean, I'm definitely available. And I think the only thing that I want to promote is actually my T-shirt.
Ooh.
So like this T-shirt is from our school, like from our group. We organize this EPW school like every year or so, sometimes every 2 years. It's usually like a presential. And yeah, if you want to learn a little bit more about like electron phonon physics, and then if you are on the field, you can definitely join the school, and we're gonna have a nice chat.
That's a cool T-shirt. Do you guys like sell the T-shirts?
There's a
Oh, that's really cool.
This was for the TAs of the
Oh, okay.
sessions. Yeah.
Okay. Yeah. Well, awesome. Thank you so
Yeah,
much.
thank you.
Appreciate it.